Hi guys, welcome to Learning Electronics Repair, and today we're going to talk about something really interesting. Well, not the way some people explain it, but this will be. And something really important about electronics. So this is Kirchhoff's law. I mentioned this on the previous video. We were playing around with LEDs and I actually demonstrated some of these principles, but this is more complete. And now I've fitted the name on the page, Kirchhoff's law. So some people call this Kirchhoff. Now I don't know which is correct myself, but I was speaking to Detlef, my friend, and he said, oh yeah, Kirchhoff, one of my fellow countrymen. So Detlef is German and Kirchhoff was German, so he pretty damn well knows how to pronounce it if you ask me. And I'm not going to disagree, so Kirchhoff's law. Actually, Kirchhoff has two laws, so there are two laws. And they're called Kirchhoff's voltage law and Kirchhoff's current law. Usually, because it's too much of a mouthful, abbreviated to KVL, Kirchhoff's voltage law, and KCL, Kirchhoff's current law. Could be KIL for current, but that sounds a bit deadly, yeah? So we don't have KIL, we have KCL. So that's the two laws. Now then, you can go and Google this stuff. Why not? Or go to, say, Wikipedia. Let me show you what you would find if you did that. And I've done exactly that. So here we are on Wikipedia about Kirchhoff's circuit laws. And straight away, it starts explaining these with all these strange, weird symbols, yeah? Like you have to know what all that means before you can understand all this means. Well, I won't call it a load of crap, but I'm not interested in any of that stuff, yeah? I'm not interested in all this gibberish. I want to just understand what it does. And I'm guessing you guys just want to understand what this does as well, without all this blah-de-blah, yeah? So we're not going to do that. If you want to do that, persuade me to do it, or just go watch somebody else do it, yeah? I'm going to explain what all this means. Because to me, this just puts me off. So Wikipedia tries to simplify this a bit. Let's see what it says. Kirchhoff's current law. It says the algebraic sum of currents in a network of conductors meeting at a point is zero. Yeah, that's what Kirchhoff says. Okay, we get a little picture with arrows and things, okay. And he then says the directed sum of the potential differences, voltages, around any closed loop is zero. That is no doubt technically correct, but I don't think that's the easiest way to explain this, to be quite honest, because I'm sure some of you are thinking, yeah, well, okay, but what does that mean? Yeah, well, why is everything zero? So let me tell you how I understand it. So Kirchhoff's voltage law. This is very simple, to be quite honest. In any circuit, we have one or more power supplies. And here we have various components. We can play with what I was playing with the other day. A couple of LEDs. Few more resistors, something like that, okay. And what Kirchhoff's voltage law actually means is that the sum of all the voltages across a circuit like this will equal the supply voltage. Whatever the supply voltage is, if that is 9 volts, and we measure the voltage across there, and we measure the voltage across there, and we measure the voltage across there, and we add them all together, it will come to 9 volts. And the same will apply here. So if we measure the voltage from here to here, and we measure the voltage across these here, either that one or that one, because they're in parallel, it will equal the supply voltage, 9 volts. So that's what Kirchhoff's voltage law actually says, yeah? The sum of the voltages will add up to the supply voltage. No more, no less, okay? Kirchhoff's current law. Well, we can use the same circuit to demonstrate this one as well. 9-volt supply. Let's do it again, a resistor. Couple of LEDs. Couple more resistors, the same circuit. Okay. And what Kirchhoff's current law tells us is that the sum of the currents flowing through the various nodes means junctions, by the way, in this circuit will add up to the overall current coming from the supply. So whatever current is going down here, okay, and whatever current is flowing through here and then through here and here, if we measure them all individually and add them up, it will equal the supply current. No more and no less. Also, from this, we can determine, and Ohm's law comes into this too, that whatever current is flowing through this resistor is the same as the current flowing through this LED, is the same as the current flowing through this LED. The current flowing through all of these is the same because they're in series like so. Yeah. So that current, if we want to call it like current, we'll use I1, yeah, current number 1. And then the current flowing here, well, whatever current is flowing here, when it gets to this node, it splits two ways. Some of the current goes that way and some of the current goes that way, and the amount will depend on the value of the resistors. But whatever current is coming into this node, this junction, will equal the current going out. So if we measure the current coming down this resistor, we measure the current coming down this resistor, it will add up to the current flowing through this one. Yeah. So we'll call this current 2, and this will equal to whatever current's on this one, called current 3, and current 4. Yeah. So current 2 will equal current 3 plus current 4. Scribbly writing, but that's what it is. And then if we add the current 1 to, well, we can just use current 2 because current 2 is the same as current 3 plus current 4. So whatever current is flowing through here in this direction and flowing through any of these in this direction will equal the total. Current total equals I1 plus I2. Or I2 plus I1, it's the same thing. So those are Kirchhoff's laws. That's all you need to know. Yeah. Unless you're mathematically minded or there's some mathematical reason why you want to know more. To understand it, that's all you need to know. And this is obvious stuff, really, if you look at it and think about it. Because the sum of the voltages in this circuit must add up to supply voltage. You can't, like, lose any energy. Energy can be neither created nor destroyed, yeah? So the sum of these voltages must add up. And the sum of these voltages must add up. It can't be anything different. And the same with the currents, yeah? Whatever current's flowing through this resistor is obviously flowing through these components, the same current. And the same here, whatever is flowing through here is being split between those two. And the total current flowing is the total current that the supplier is supplying, yeah? Not difficult, is it? But now I want to talk about something interesting. Yeah. You see, we have in modern electronics a lot of circuits that run from low voltages. So we normally have a higher supply voltage, 12 volts, 5 volts, 9 volts, something like that. And circuits, microcontroller or microprocessor type circuits running at 1 volt or 0.9 volts, 1.2, 1.5 and such like. And that means that devices these days contain a lot of these sort of circuits. A lot of people call this a buck converter. It's not actually. It's a synchronous converter. So we have a circuit. This is your positive. This is your negative. You'd find this, for example, driving the GPU on a graphics card. In fact, there'd be a number of them in parallel, forming what is called a VRM. okay, voltage regulator module. And we have a supply. $12 volts, okay. And we have here a couple of MOSFETs. And these are connected to a controller, pulse width modulator, okay, like so. And from here, the junction, we have an inductor coil. And here we have a capacitor. This is the output capacitor. And then here we have the load. Whatever device we are supplying with power. And typical with one of these things, this might be 12 volts and the load might, for example, be running on 1 volt. Okay, so the way this circuit works is that the controller switches this MOSFET on, and this allows current to pass through the inductor into the load. Now, there's a rule or law that is involving inductors and capacitors, and that's something we call civil. Okay, and this means for capacitors, the current I leads the voltage. So when we charge a capacitor, before the capacitor holds any voltage, we must put current in, we must charge it. That's fairly obvious, yeah. The other one, voltage leads current in an inductor. So with an inductor, before any current can flow through it, we have to apply voltage to it. So basically, when this MOSFET turns on and the current flows this way, the voltage appears across the inductor, 12 volts this end, 0 volts on that end, or if the capacitor's already charged, 1 volt on that end, so there's 11 or 12 volts from here to here. Okay, current flows in and that magnetizes the inductor. It builds up a magnetic field. The idea of the VRM is before the voltage can appear on this end, we switch the MOSFET back off again. What happens now is we switch this MOSFET on and the magnetic field collapses in the inductor, and that pushes voltage, or rather current, in the same direction, charging the capacitor and supplying the load. So it's the collapsing magnetic field that powers the load. By the time the magnetic field has collapsed, we switch this MOSFET off and this one back on again, and again current flows in and it magnetizes the coil over and over again. And this happens at high frequency, hundreds of kilohertz. Now look at this from Kirchhoff's point. So Kirchhoff's current law. We have coming in, let's say we have 10 amps. So this load is taking 120 watts, thereabouts, allowing for efficiency and losses. But let's say that the current flowing into the inductor is 10 amps. So we have 10 amps flowing down through here, okay? This converter is a DC to DC converter, and what actually comes out is, for example, 1 volt at 100 amps. 10 times as much, okay? In fact, no, let's say 120, because we'll get the maths right. So 1 volt, 120 amps. So we've got 10 amps coming into here and 120 amps going that way. Yeah, and 10 amps going this way. That's supply. So what does Kirchhoff's law say about this? Because the current flowing into this node and the current flowing into the load does not add up to the supply current, because the supply is providing 10 amps. So we've got supply giving us 10 amps going in, but we've got 130 amps coming out. Yeah. Is Kirchhoff's law wrong? Well, actually, it isn't. I haven't done something clever here. It's not like we've invented something that Kirchhoff didn't have. these circuits. I asked Detlef about this, and that's why I made this video, because I said, hey Detlef, what does Kirchhoff's law say about this? How come the current doesn't balance up? We have a 10 amp supply and 120 into the load. Yeah. And he said, oh, well, I've only ever seen Kirchhoff done with resistors. Maybe it doesn't apply to inductors and such like. Well, actually it does. And when I explain to you now, if this puzzles you, because it puzzled me at first, it makes perfect sense as well. What we have here is a very good example of a phased circuit. So this circuit has two phases. The two phases are the phase when this MOSFET is switched on and this one is switched off. That's when we magnetize the coil. And the phase when this one is switched off and this one is switched on, that's when the magnetic field collapses, charging this capacitor to keep the voltage level and also supplying current into the load. And you may, if you think about it, wonder, why do we need this MOSFET? Why can't we just keep pulsing this one at high frequency with a pulse with just the right width to give us just enough magnetic field in the coil, so when it collapses, it powers the load and charges the capacitor? Well, the reason for that is also the fact this circuit has two phases. So let's have a look to see what actually happens. Okay, in the first phase, we magnetize the coil. So this MOSFET is switched off. So let's put a finger over it like I just did. That is not there during this phase. So what circuit do we have? Well, we have that circuit. Okay? And the current flowing through this circuit must equal the current from the supply. If you've got 10 amps coming in, there's 10 amps going out. Exactly. That's Kirchhoff. KCL. Kirchhoff's current law. And that's what we actually have. So at the time this is switched on, we have a 10 amp supply. Okay? 10 amps coming in, 10 amps going out, if you like. This isn't here. It's switched off. We can ignore it. So that's the first phase. And to complete Kirchhoff's law, because we should do, the 10 amps flows back here, back through the supply, and back to there. It's a closed loop. Okay? What happens in the second phase? Well, in the second phase, this MOSFET switches off. So that is no longer there. This circuit is broken. It's no longer there. In phase 2, this 10 amp circuit doesn't exist. What circuit do we have? Well, we have the collapsing magnetic field. So now, this coil, this is the power supply. Yeah? Giving positive on this end. Where's the circuit? Well, it's from this end of the inductor, through the load, back here, through the MOSFET, and back to there. There is the circuit. And this is our 120 amp circuit. Okay? So what we actually have here are two circuits. Although it's all interconnected, from Kirchhoff's point of view and from the circuit operation, we have two circuits. That's why it looks initially like it isn't obeying Kirchhoff's current law. It is. It's just switching so rapidly between the two circuits by switching these on and off. Maybe your mind can't think fast enough to realise that's what's happening. Okay? Last thing I mentioned, this is not a buck converter, it's a synchronous converter. If it was a buck converter, okay, it would look like this. Okay, That's a buck converter. Pulse width modulator. In this circuit, we only have one MOSFET. It does the same. This either switches on to magnetize the coil or switches off to stop magnetizing the coil. We still have two circuits. So we still have the charging circuit, if you like, what we call our 10 amp circuit. And we still have, from the coil back through this diode, notice in this direction this is forward biased, okay? This end is more positive than this end because this is now the positive supply, the coil, and we have that circuit. That's a buck converter. This one is a synchronous converter. You can see we don't actually need that second MOSFET because this diode only conducts in one direction, so it automatically completes the circuit whenever this end of the coil becomes positive with respect to that end. In other words, when that is switched off. Why don't we see buck converters very often? Well, even if this was a Schottky diode, which it probably would be, there is some voltage drop here. So for a normal diode, it's about 0.6 volts. For a Schottky diode, maybe 0.15 volts. But there is some voltage drop across the diode, which means there is some loss of efficiency due to the voltage drop across the diode. Okay? A MOSFET, when it's switched on, can have an extremely low drain source, extremely low RDS, resistance between the drain and source, much lower than a Schottky diode, so the voltage across there is much lower than the 0.15. Okay, this resistance when it's on could be as low as 8 milliohms, something like that, maybe even lower. So that's why we use the synchronous converter rather than the buck converter, mostly because it's just more efficient. So there we have it, Kirchhoff versus the VRM. And Kirchhoff won, yeah, or at least, shall we say, the VRM didn't beat Kirchhoff. It's not doing anything magical. There's no unicorn here. It doesn't break the laws of physics. As Scotty said, you can't break the laws of physics. Hope that cleared some things in your mind, because it took me a little while to figure out that one. Let me know in the comments below, and I look forward to seeing you all soon on another Learning Electronics Repair video. Ciao for now, guys.